So today is kind of like lecture 2 of our discussion of neural networks, okay? So last time we kind of talked about the general idea of what is a neural network, and today what I want to talk about for most of the class is this critical algorithm called backpropagation, or backprop. So basically, this is the way to optimize the parameters of a neural network, and it basically is under the hood of every modern machine learning system, right? So ChatGPT was trained using backprop, right? And so it's good to know this. And so let's just talk about, the setup. So this is from last time, right? We have a bunch of inputs, which we can call X. These go through, some number of hidden layers, right? So I'm not going to draw all the connections, but basically, I have connections like this. Maybe draw this guy, right? So these here are what you would call hidden layers. And then over here we have our outputs. And so let's call those Y, okay? And so again, if we kind of zoom in on what's happening at a single one of these dots, what do I really mean when I have this picture, right? So let's kind of zoom in here. So at a single neuron, let me be a little more specific about what's going on. So we have several inputs, and we have a node, and so these inputs are all coming into this node with weights. And there may be an additional bias term where we add a constant to this set of linearly weighted inputs. And then the critical thing that makes this work is some sort of a nonlinear function. And then the output is the result of this linear combination of inputs processed by some sort of a nonlinear function, and then I get my output, okay? So that's the setup. And so we have a selection of weights and biases at every node of this network that could be several layers deep, right? So we have to optimize all of those numbers at once to find the best answer. And so what are we optimizing, right? So we have a cost function, right? So we have an error function. That we're going to assume basically looks like, the error for a given possible set of all these weights is adding up the errors for each of the n training samples. Right, so if we're doing a regression problem, then this error could be like the, squared error. If we're doing a classification problem, this could be like the cross entropy loss, right? But the idea is that basically we're summing that up over all of our training samples, okay? And we know that we can minimize this cost function by some form of gradient descent, right? So we can minimize using, and again, I'm going to say SGD, right? Stochastic gradient descent, where fundamentally we update the weights by taking a step in the direction of the gradient of one of these cost functions, right? And of course, there are variations on this. You could do a mini batch or something like that, where you're looking at the average of some gradients. This is the most basic idea, right? Okay. So there are, of course, other options besides exactly using stochastic gradient descent to solve this problem, but they all depend on computing the gradient of the cost function, right? So, the key idea, the key issue is we must compute the gradients. No matter kind of how we minimize things, we have to deal with figuring out this item, okay? And so that's what backpropagation is about. And so actually, there's nothing really new about backpropagation. It's really just a kind of a simple observation about the way that derivatives at a certain layer depend on derivatives from another layer, right? So in some sense, it's just a fancy version of the chain rule, right? So the chain rule from calculus that you learned, years ago is fundamentally what we're doing here today. So it's just like chain rule applied to gradient descent is what backpropagation kind of fundamentally is. Okay, so let's dive into it, right? And so this is going to be a little bit, tedious, but hopefully you'll get the idea. So let me start with a very simple example of a network, and then we can kind of derive what these gradients should be, right? So let me just say that, what am I talking about? So the algorithm we're talking about today is called backpropagation. And really kind of its full name would be like the error backpropagation algorithm. And often you'll see it casually called backprop. Is a way of efficiently computing the gradients we need via the chain rule, basically, from calculus. Okay, so let me draw a simple network with an input layer, a hidden layer, and an output layer, and think about what sets of weights and so on we have to deal with, okay? So, and let's assume that, biases are kind of built into the network, so all I have are weights, and I'm not worrying about the bias stuff. So here's an example. So let's suppose that I have inputs. So x1 through xd, okay? So these are my inputs. Then I'm going to draw a hidden layer that has m nodes, z1 through zm. And I'm going to assume that these are all connected. Now, I will mention today and also on Thursday that it's not necessarily required that everything be fully connected, but oftentimes when we talk about when we talk about a multi-layer perceptron, which is what we introduced last time, usually these are all fully connected like this. We'll talk about something on Thursday that is not fully connected called a convolutional neural network, but for the moment, let's just deal with this, okay? And so we have these are my kind of like hidden layers. And then these are processed to produce outputs, right? So let's call these y1 through yk. Okay, and now let's be a little bit more specific about where each of these numbers is coming from, right? So I know that I'm going to obtain z by doing a linear combination of the x's and then pushing that through some sort of a nonlinear function, okay? So let me just do an example here. So let's suppose that what's coming into this node beforehand, let's call these the a's, right? So let's say we have aj is the sum from I equals 1 to d of some weights at the lower layer applied to the inputs, okay? And then zj is, for example, going to be a nonlinear function. Today I'm going to introduce what's called the tan-h function, and I'll write this down on the next slide. But this is basically some nonlinear function that processes this linear combination to turn it into the z. And then, to get the yi's, let's suppose that, let me just kind of draw a box around here so I'm not getting too messed up. Let's suppose that then the yk is just a linear combination of weights times the z's. Okay, so I'm going to leave this, so I'm not even going to put another nonlinearity at the end. I'm just going to leave it as a straight out linear combination, okay? And then we have a cost function, right? Our cost function for the nth data point is basically the difference between the output of the model and some target variable, right? I guess it should be like yk sub n target k sub n. So this is like saying that I have like a k-dimensional output variable, and I have one of those for every sample from 1 to n, right? So here, this is basically like, you know, k-dimensional model output, and this is like a k-dimensional target. And so we're trying to minimize the difference between the model and the target. And that's the, you know, contribution to the error for the nth sample. All right, so before I move off of the slide, yes, question?
Is that yk to the n? Or is it
It's like the nth instantiation of yk. So it's not to the power, it's kind of like a little parentheses, right? I could have put this somewhere else. I could have said like y sub nk or something like that. As I was writing it, I realized I had to have an n somewhere, so that's what I did. So this is like solving basically like a regression problem, where I'm trying to bring the vector of y's as close as possible to the vector of t's, and that's kind of what makes sense to minimize, right? If I was doing just like a, you know, binary classification problem, then really the only output I would need would be like one value of y, right? As I could think about like a logistic regression output, like just either a probability, or it could just be like a, you know, a 0 or a 1 at the end, right? But here I'm kind of doing it in a more general way, okay? So now what I need to do is think about how do I take the derivative of this e with respect to the things that I don't know, which are these weights, right? So I have these w's and these w's that I need to minimize over, right? And so it should be pretty clear that it's not too hard to think about, right? So here, the wji's are kind of the first layer of the network, and the w prime kj's are the second layer of the network, right? So it's not too hard to take the first derivative, but we'll have to take another issue kind of going back as we push down to lower layers of the network, okay? And so let me just write down what I just said. So we will need, basically, we need to compute the partial derivative of this contribution to the error with respect to these weights and the partial derivative with respect to weights. Now, one thing to observe is that, you know, in order to take the derivative, and I think that you already saw this, like for example, on the exam problem where we're looking at gradient descent. So I need to know what does the model output for this point, right? So I need yk to be able to even evaluate the gradient, right? So that means that I need to push the data through the network first, right? So we were talking about last time that you can think about this as what's called a feed-forward network, right? So here, I push the data through from left to right to go from inputs to model outputs y, right? And then, as the name implies, the backpropagation algorithm is going to be computing gradients, but pushing it back from the, you know, y end of the network all the way back to the beginning, right? So first we're going to compute the derivatives with respect to the w primes, and then we're going to compute the derivatives with respect to the w's, okay? And that's why it's called backpropagation, because we're basically pushing stuff back through the network. So again, let me just write that down on paper. So to compute the yk in the first place, we need to, you know, kind of what you call forward propagate through the network. Like we actually have to evaluate these outputs. So a key idea here that makes this whole thing work is that everything we've set up is differentiable, okay? So here, for example, we're taking derivatives with respect to the w's, right? So here, clearly this is differentiable with respect to w. This is differentiable with respect to this. The only thing that's a little bit of a question mark is what is this function here? Let me just write down what this tan h function is. So tan h is a function that looks like this. And I think I introduced it last time. So kind of like the sigmoid, it pushes any value on the x-axis to a value that's either, a value that's between +1 and -1 on the y-axis, right? And the definition of it is the following. E to the a, oops, I already messed this up. E to the a minus e to the minus a over e to the a plus e to the minus a. So it's an easy function to write down. And so since everything is exponential, it's easy to take the derivative of this function, right? So it's the way I learned it was ho d high minus hi d ho over ho ho. So ho d high minus hi d ho over ho ho. And one nice thing that you can see, actually, if you write this stuff out, is that actually a lot of stuff cancels, right? So for example, I'm going to have a e to the a times an e to the a here, but I'm subtracting that off. I'm going to have a e to the minus a times e to the a. That's just 1, right? And I have another 1 here. Actually, this whole thing just turns out to be very simple. And you can show that this is related to the original function by this. This is just algebra, so I'm not too stressed out about it. The point is it's differentiable, right? So if a is the input to the nonlinearity, I can take the derivative with respect to what comes in, and I get this simple thing. So we're going to use this later, okay? And again, you should be able to convince yourself, like, why does the function look like this, right? So if I put in plus infinity, right, I basically get, these things go to 0, and I have basically the ratio of something big to the same something big that kind of goes to 1 at this end. If I have minus infinity, then I basically have, this goes away, and I have something converging to -1, right? So you should be able to convince yourself that this is why the function looks the way it does. Okay, so now let's actually take the derivatives. Like, we're going to do kind of like one step of backpropagation, okay? So what I need to do is I need to take the derivatives of let's start with the wkj prime, right? Referring back to my picture, I'm thinking about what's happening to the derivative of the cost function with respect to the stuff that's happening at the kind of back end of the network, right? Well, this is just like saying I'm going to take the partial with respect to wkj prime of the cost function that I have. And again, this is kind of like the, the nth sample, right? So again, I'm kind of not going to write the parentheses n here all the time, just to kind of indicate that, I'm using this with respect to just the nth sample, okay? And now, what's this derivative? Well, here, this is not so bad, right? If I refer back to how is y related to the w prime, well, this is just going to be the z, right? So if I write this down, this is going to be yk minus tk. 2 times this cancels that 1/2 out. And then I have the derivative of yk with respect to this weight. And that's like saying, well, this is only going to depend on, if I'm talking about like one of the wkj's, like say I'm talking about like wk sub 2, that's only going to depend on this link from this node over here. So even though there's a sum here, the thing that drops away is only the jth element, right? So this thing is basically like saying, let me just write this over here. So only the kth term involves wkj prime. And then what is this value here? I go back and I look at my formula, right? This is how yk was obtained. Take the derivative and I just get this z, right? So it's like saying that I have this difference times zj. And I'm going to give this guy a name. I'm going to call this little delta k prime. So what is the kind of key idea here, right? So the idea here is that this part here and this is basically the error at the output, right? Because I already propagated the numbers through the network, I can evaluate how far off my model currently is from the target, right? So that's what this term is. This is like an error term. And this here is like the input to the node. So if I look back at my picture, this is like saying that what I'm doing to compute the derivative is I'm looking at the error coming into this node, and I'm going to look back at what the input was to that node. So there's an error part and there's a z part, right? So that's kind of like the key idea. This is like the error at output times the input to the node. And the reason I'm writing it this way is that we'll see that at the next layer I have something that looks basically the same, okay? So that was an easy derivative to take, right? So it's not hard for me to evaluate the derivative. One thing that you have to observe here is that to compute the derivative, I really need to be keeping track of all the intermediate stuff, right? So after I compute this z, I don't want to throw it away to compute these things. I want to hold on to it because I'm going to need it to compute the gradient, right? So in any sort of modern like neural network optimization, you are kind of preserving, okay, some intermediate stuff in the network that I had to compute anyway on the way to the output, and I'm going to save that stuff to make it easier for me to compute the gradients later, okay? So let's just say that we make sure to save this. And again, I'm sure that you're thinking, oh my God, he's not going to make us actually implement this, and I'm not going to make you actually implement this, right? But this is the way it actually works under the hood. Yeah?
So if you have like a 5-layer network, you'd save every layer's perceptron's values?
Yes, so if you had a 5-layer network, you have to save the output, or you have to save the input to every next layer, right? So that's exactly what you have to do, yeah. But again, well, I mean, that's just bookkeeping, right? You have to do it, yeah. Okay. Other questions or comments? So this derivative was pretty easy to take because if I'm thinking about it, like the only, if I want to take the derivative of one of these numbers with respect to this weight, it only depends on one of these branches, right? However, now if I want to take the derivative with respect to one of these weights, I can see that this guy is going to contribute to this, which is going to contribute to all of these things, right? So there's going to be a little bit more bookkeeping to do to go backwards into the network. So let's write that down there. So so to compute the next derivative, partial e with respect to the one layer back, this only depends on the jth value of z, which is one of the hidden nodes. And then by the chain rule, what I'm going to compute is the partial of e with respect to this guy here. Well, I'm going to say, okay, that depends on zj. And then the zj partial depends on what comes into that node before the nonlinearity, which is what we call AJ, the activation, and then the derivative of the activation over the weight here. Okay? And so now we have to actually figure out what each of these three things is. And it's, again, not too bad, right? So let me compute this guy first, right? So I'm going to keep this on the board here. So this is like saying that the partial of E with respect to Zj, that's the first thing I want to compute. Well, it's the partial of, again, this sum, yk minus tk squared. Take the derivative. I still have the sum because now I can't kind of reduce the thing down. So the 2 cancels with this 2. And now what I need is the partial of yk with respect to zj. And this is, again, looking at my thing here, this is like saying, well, yk and zj are related by this one weight here. So this is like saying I have yk minus tk times this weight. And again, I can kind of make a new abbreviation to say this is like what I called delta k prime before, so I have that saved, times this weight. So again, one way of thinking about this is that this is kind of like saying that the derivative for this z is kind of like a weighted combination of the errors at the last stage of the network, right? So here, this is like a weighted combination or weighted sum of the errors at the last stage of the network. And again, it takes some time to really internalize this. So after my lecture is done, I encourage you to go back and read the backpropagation chapter of the book, watch a video on backpropagation, kind of like, again, try to find the way to make this kind of solidify in your head a little bit. All it is just taking derivatives at the end of the day, but it can be a little bit confusing because there's lots of notation, right? And then, now that I've computed this part, I just need to compute these things, right? So the partial of z with respect to aj, that's like saying, what is the derivative of the activation function based on what comes in? We discovered before from, I did this already on a previous piece of paper, right? When I first introduced the tan h, I computed, what is the derivative of this thing with respect to its input? It's 1 minus that thing squared, right? So that's exactly what I'm doing here. And then the last thing I need is what is the derivative of the aj with respect to this weight? Well, this is just, again, if I go back and look at what I define as this is just a linear combination of the inputs. And so all I have to do is just take the corresponding input. This is just xi. So putting it all together, I have to multiply these three terms together. And what do I get? What I get is the partial of E with respect to Wji is this term, which is a little bit off the screen, like this guy. Times this thing times this thing. And again, I can kind of interpret this by saying this is like, I'm going to call this delta j times xi. Again, this is kind of like a weighted combination of previous errors. That's what this part is, times the input to the node. So the idea is that at every layer of backpropagation, you can kind of think about it as the input to the node, where that weight is involved, times the error at the other end, right? And so this obviously will change depending on how many layers you have, what types of activation functions you have. Like if I use a different function, like if I use the sigmoid instead of the tan h, I would have a slightly different looking derivative at this point, right? But the basic idea is that we're backpropagating errors from the one end of the network all the way back to the beginning. And now at this point I would stop because I'm done. I've computed the two derivatives that I would need. That would enable me to take one step of gradient descent in the direction that I need to, right? And so, it's just a long and tedious derivation of the chain rule that tells me how these things are hooked together. And so by some clever bookkeeping of keeping the outputs at different layers of the network and the inputs, I can kind of push those errors back without doing a whole lot of extra computation, right? So that is the wonder of backpropagation, okay? So that's all it is, really, and so on. So this basic idea continues if we have more layers, different activation functions, and so on. Really all I'm doing every time is I'm weighting the previous errors, multiplying them by the input. And so really, this is like one example with a simple regression cost function. I could do the very same thing if I had a classification problem, which had a different function, a different form of E, right? All of it would be the same. So your most complicated, transformer attention, network, is going to be minimized using the same fundamental idea of backpropagation, right? So I think it's worth spending one lecture or half of one lecture on what's actually going on under the hood. So let me pause and ask questions or comments about this. Again, you need to do a little bit more offline study to kind of really get it, but that's the basic idea, okay? Now, as with any sort of like real world numerical problem, there are a lot of rules of thumb and heuristics that you need to make this really work well in practice, okay? So what I want to talk about for the rest of today's lecture are kind of just like some of the tips and tricks that you would need in practice and things that are really under the hood of a modern machine learning optimizer that will make it all actually work, right? Because if you were just to implement this like straight out, you have a lot of decisions to make, right? Like you have to decide, for example, like what should the step size of your gradient descent be? Where should you start your optimizer? Like there's a whole bunch of possibilities, right? So that's what I want to talk about for the rest of the day are some, heuristics to make backpropagation work. So heuristics to make backprop work in practice. So critical idea is the initialization of the weights. So this is important because if we were just going to initialize everything with like 0, for example, if I look at this, like if I initialized all these weights with 0 and all these weights with 0, then the output of the network would be 0, and all my errors that I'd push back would be basically multiplied by zeros. And so fundamentally, the network would never do anything, right? So I have to have a smarter idea than that, right? So, can't just initialize with all 0 because then basically, the backprop errors would all be 0 and nothing would ever converge, right? I mean, nothing before the last layer would ever change, is maybe a better way to say it. The last layer might change, but the previous layers wouldn't change. So a common thing to do is to initialize the weights as, random uniform, well, maybe I should say uniform random variables. On the range minus d to d, where d is related to the number of neurons connected to a node. Again, these are not like hard and fast rules. There are many ways of doing it, but this is one kind of standard way of doing it. You look how much stuff is coming in, and you make a uniform random variable that's related to that number, okay? Again, as with any optimization, you may need to evaluate what would happen if you use different initializations and you do 10 runs through the network and you take the one that gives you the lowest training error, right? Because there's no guarantee that the place that you start will lead you to the true global minimum because you're doing this kind of stochastic gradient descent problem, right? So that's one kind of thing that's really important, is just initialization in general. Another thing that's really important is what I would call scaling issues, right? So one thing I would say is that normalization is important at the input stage. Right, so say for example, I'm taking my input variables and there's like a mass and there's a length, okay? So if I measured the mass in milligrams and I measured the length in meters, right, then my length would be very low numbers and my mass would be these very huge numbers, right? There's an imbalance in the scale of the inputs, right? And that can cause problems later on in your network if all the input variables are not scaled in the right way, right? Maybe you observed this on homework 3, where you had these points in the image plane that were kind of on the scale of hundreds. I had talked to someone in office hours where we realized that if you solved the problem in a certain way, the matrix that you were using had like values that were in the billions, right? And so it was a poorly conditioned problem, right? So we want to avoid those kinds of numerical problems. In theory, if you had infinite floating point arithmetic, there wouldn't be any problem at all. But in practice, you want to avoid these kinds of like numerical overflow, underflow problems, right? So typically what you would do is to, so typically on a per feature basis, we apply something like the following. I take my old feature and I subtract off the mean and divide by the standard deviation, right? So here the mean is like the expected value of x, and the sigma squared is the variance of x, right? In this way, if I kind of take this row of inputs and I subtract off the mean, divide by the standard deviation, what happens is that now the expected value of this new feature is 0, and the variance of this new feature is 1. So all of these input variables are now basically on the same scale, have the same variation, they're all well behaved. The only thing you have to remember to do is to make sure that you apply that same transformation to the testing data before you put it into the network, right? So just remember to, also, also apply the same transformation to the testing data. And actually, in general, whenever you're solving a numerical problem, this kind of normalization is a good thing to do, period, right? So if I had carried that much, I probably would have asked you on the last homework to also normalize the inputs before you tried to learn this phi matrix. You would have gotten the same answer, but it would probably would have numerically better. And so in theory, you probably also want to apply similar normalization to the output variables, but the input variables is definitely important, right? So Questions or comments about this? Okay, so another thing that's really important to think about is the activation function, right? So the activation functions make a difference. And again, I don't want to turn this into a deep learning class. Some of the stuff I'm talking about here, you would probably talk about in a lot more detail in deep learning. But the basic idea is that what I want is some sort of a function that scales any real number into some finite range, like plus or minus 1, right? So this is like the hypertan function. And the nice thing about this is that when the error is small, right? So when error is kind of close to 0, the function is basically linear, right? That's like saying that when I'm kind of close to the answer, then, what the active function is doing is more or less not doing anything super nonlinear at all. It's just kind of like proportional to the magnitude of the error. The bigger problem is what happens over here at the other end, right? So over here, suppose I have some really big error, right? So this is like a big error. If I push that up to where the function is, then at this point, the derivative is basically 0, right? That's the problem, right? That's like saying that at some point, I need to take the gradient of this activation function, and that gradient could be 0 or very close to 0, which means that suddenly, as soon as I hit that problem where there's a big error at that node, the 0 problem with the gradient will push back and cause problems every point further back on the network, right? This is called the vanishing gradients problem, right? So this is called, big error may produce what are called vanishing gradients. Ooh. That's the problem over here. And the result is that the weights that you're trying to change at lower levels of the network are not going to change very much at all because this number is so close to 0, right? So what that means is that it may be hard for large gradients to propagate back into lower levels of the network. So let me write that down. So it may be hard to propagate big errors down to lower layers. So one solution to that could be, okay, maybe I don't want to bound my gradient at all, right? So what I could do instead would be, I think I mentioned it last time, an alternative activation function is called the ReLU, rectified linear unit, whose looks like this, basically, right? So here, this is like saying, well, if there's a big error, then there's going to be a big gradient, right? So that will definitely push those gradients back, but this also may have other numerical problems, right? Because suddenly I may have like huge numbers floating around in my network, right? So here, this says that if I have a big error, then I also have a big gradient, but may cause other problems. Right? There's something called exploding gradients. Oh no. So honestly, training a neural network, especially a large neural network, is this kind of black art of trying things, changing your activation function, changing your step size, kind of like, it's definitely not uncommon for you to try some default parameters for your neural network, train it, it doesn't converge, right? So it's like, what do I do? Well, I tweak some stuff, right? Maybe I want to use ReLUs this layer instead of tan H's and see if that makes the day better. Unfortunately, there's no real mathematical down from the heavens like commandments about how to do it so it will always work, right? It just takes time, and I'm the first to admit that I don't have the intuition personally to know how to tweak these neural networks, but I think when we have our panel of students next Monday who are going to talk about their real research problems, we can ask them this question, right? Like, so when you're training a neural network, how much do you have to screw around with it to make it work, right? Luckily, modern packages probably have a lot of great heuristics that are internalized into it, so you don't have to make those choices too much yourself. It's a lot easier today than it ever was to get a network that will converge, but in practice, there's probably still some sort of personal intervention you have to do. Okay. So one thing we talked about. Question.
On the previous function, the issue with the derivative being equal to 0. What was the? I'm just confused on the issues with that the vanishing problem.
So the issue is that basically at some point what we're doing is we are multiplying by, like, so this part here, for example, this is the derivative of the activation function. If this number is 0, then this number becomes 0, and that means that the weight is not going to change because the gradient is 0 in that direction, right? That's the issue. So if one of these numbers becomes very small, then this whole number becomes small, and nothing ever happens as I go backwards, right? That's what's called vanishing gradients. Does that make sense?
Yeah.
Okay. Was it? Yes, nothing will ever improve if the step, so if you're taking a step in the direction of the gradient and the gradient is 0, right, that means you're not going to move in that direction, right? Yeah. Okay, so there's this. Another thing we talked about before at the very beginning of all the classes was this issue of overfitting and not being able to generalize, right? So the common problem is basically overfitting leading to poor generalization. So that means that things look great on the testing set, and then you bring it over to the training, things look great on the training set, you bring it over to the testing set, and it doesn't work very well, right? That means that you've really overfitted to your trained data, but it doesn't work on any other data, right? So one way to combat this, which is what we asked about in exam 1, is what's called regularization. Right? So regularization is changing the cost function to have some sort of an additional thing that has nothing to do with the data, but only depends on the weights themselves, right? So here, this is like saying, how good is the data fit? I want that to be small. But this is basically saying, I want the weights to also be small. So this encourages the weights to be small. And if you remember, we talked earlier about how this could be interpreted like a Bayesian prior, that the weights should be small to begin with, okay? So once you start to think about this in some detail, the problem with this is that, I have potentially hundreds or thousands of weights inside my network, and this is basically weighting, I'm using too many of the words. So this is basically saying that every one of those weights has equal emphasis lambda. Whereas if you think about it a little bit, it seems like maybe I should be kind of like putting emphasis lambda 1 on the weights that are close to the end of the network, and emphasis lambda 2 on the weights that are in the middle, and emphasis lambda 3 that are at weights towards the beginning, right? So I shouldn't necessarily be weighting everything with the same single scale factor. So let me just say that, to do this right, I probably should have different lambda for different layers, which in itself is not hard to do, right? You just kind of have, instead of this, I have like lambda 1 times some weights and lambda 2 times some other weights. That's okay. Also, one thing to think about is that, if I were to rescale my data, right? So we were talking about this issue of like millimeters versus kilograms before, right? So if I were to change how I scale my input data, that will also have an effect on what these weights are, and maybe the lambdas shouldn't have to be tuned depending on how I scale my input. So kind of what I'm saying is that also, you know, the regularization that you use should be invariant to how the input is scaled, right? And so again, that's kind of tricky. Not something that I want you guys to worry about so much in here. I'm just trying to bring up some of the common issues, right? So even though we talked about this as regularization, in practice, it's never as easy as this, right? Because you have to think about these kinds of issues, right? So the Bishop book has more kind of like information and rules of thumb about what the right way to regularize is under different circumstances, right? So if you're really interested in that, then you can kind of go into it. Okay, so that's one thing that you can do. Another thing that you can do to combat this overfitting problem is what's called early stopping. So another approach to overfitting is what's called early stopping. So kind of the idea is that, you know, if I have, you know, some sort of a training process, as I train, you know, my error is going to go lower and lower, right? But as we talked about, if I go all the way to here, what that may mean is that I have overfit to my training data, right? So maybe what I want to do instead, and we talked about this earlier, is to have what's called a validation test set, right? So I could have a training data set, and I could save some of that training data off to the side and call that a validation set, right? And so what I may see on my validation set is that the error goes down for a while, but then it starts to go back up again because this is what happens when things are being overfit. So if I call this the validation data, what I may do is I may stop, you know, at this point. The idea being that I don't run the training data to completion. I kind of have a holdout set that's kind of like a mini testing set that I wait until I hit the minimum of that. And once that starts to increase, I say, okay, I better stop, right? So that's another way to kind of prevent overfitting or to mitigate overfitting. And again, there's lots of black art in terms of like, well, how big should this validation data set be and so on, right? There's no single answer, but that's kind of like the basic idea, okay? All right, what else do I have to say? Okay, so one thing that is also kind of, so I kind of talked about invariance, right? So I talked about invariance here. What that means is basically that if I change the inputs in some way that doesn't significantly change the problem, then my output results shouldn't change significantly either, right? And one thing that you're going to come up with is that, you know, for example, I do a lot of computer vision type stuff, right? So, you know, another type of invariance that we want is to slight transformations of the input. Right, so suppose, for example, I'm doing a number recognition problem, right? So, you know, I'm feeding nice number sixes into my network. Well, you know, I kind of want my network to do the same thing if I move the 6 over here, or if the 6 is like a little tilted like this, right? Things like translation, rotation, scaling of the input shouldn't cause the network to, you know, to cause the network to create significantly different outputs, right? So for example, here, this is like, you know, translation, rotation, scale. I still want my neural network to come out and say 6 at the end, regardless of how the input is kind of placed, right? So there are a bunch of ways of dealing with this problem, right? So one way of dealing with it is what's called, convolutional neural nets. We're going to talk about that in some detail next time. So convolutional neural networks. These are basically a way of creating a neural network where this invariance to the input, at least in terms of translations, is kind of built into the way we create the network in the first place. So that's why CNNs were actually very popular in the beginning, was that they were robust to these shifts in the input, okay? So this is kind of like built in to the design. That's one way you can get this invariance. Another thing that's super common is on the input side is what's called data augmentation. So what this means is that you as the user are doing this kind of process by feeding all the little slight changes in the input that you think might happen into the network as you train, right? So maybe you only have these nice hand-drawn sixes, but then what you do is you randomly translate the sixes around, you randomly rotate them a little bit, maybe you add a little bit of noise to them, and in that way, you are trying to make your network more robust to all these possible variations in the input, right? So this is basically saying the user basically replicates the train data with different transformations themselves. And actually, to be honest, even if you aren't really worried about these kinds of things, it's still a generally good thing to do, especially when, as in the real world, you'll find that many times you don't have as much data as you want, right? So I don't know how many meetings I've been in where someone who doesn't really know a lot about machine learning, they have a relatively small problem, and they say, okay, let's apply machine learning to solve this problem, right? And they only have like 100 data points. And so I'm like, well, that's not enough to train like a modern neural network, right? So what you can do, I mean, it's still not great, but what you can do is try to augment your data by shifting it around and noising it up and moving it up and moving it down, right? So you may find that for your own projects, you may have to do some data augmentation yourself just in order to get enough data to train a larger network, for example, if that's what you want to do, right? So this data augmentation is very common, and again, it's built into a lot of machine learning algorithms, or not algorithms, packages by default, right? There's probably just like a little function that says data augment, and you specify what kinds of augmentations you want, and it will just like do all that stuff for you automatically. You don't have to manually move all the stuff around, right? So yes, you could do this. You could add noise. Noise often, if you add some noise in the beginning, makes things more robust. Okay, so that's one thing. Another thing that may work to make your machine learning training work a little bit better is what I would call hints, right? So let's just say that hints may make the performance better. And so kind of what I mean by that is that the goal of a neural network is hopefully for you as the user not have to guess what good features are for your input, right? So you're hoping that the network will learn inside all these hidden layers what are kind of like good transformations of the input that are predictive of the output, right? But sometimes it may help to give that a little nudge, right? So for example, let's suppose that you are trying to convert spoken speech to written speech, right? So speech to text. So what you may do, for example, what you want to do is you may have a sound, and the sound comes in and it has a whole bunch of input features, right? So you might imagine that these are like, Fourier transforms of the input at short time windows or something like that. You put this into some sort of a big network that has a zillion hidden layers in it, and then what you want to come out of the network is basically like what are called phonemes, right? So phonemes are the little sub parts of speech, like little sounds, like ba, ka, whatever, right? And so that's kind of what you want the network to do. What you may do during training to help this network along is you may add a couple extra nodes, right? One node that says vowel and one node that says consonant, and this is like a one-hot pair of output nodes, right? So kind of what you do is you say, okay, when I'm training, I know what the true phoneme is, and I also know what vowels and consonants are. And so I kind of make my network learn that stuff. But then when I actually apply the network, I just throw away all the weights that are connected to these things, because I don't really care about that for the purposes of writing down the phoneme. But I'm hoping that by including this, the network has learned something useful about what vowels and consonants are that help it do better on the job at the first part, right? So you kind of may give it a little bit of a nudge to say, hey, I think that this other aspect of the input data is important, and so I want you to learn that too, and then you throw that away at the end, right? So again, this is like super problem specific, but in practice, it may help your network do better, okay? All right, 2 more things, and then we'll be done for the day. So, and these 2 things are actually things that we already kind of talked about when we talked about gradient descent, right? So a critical issue, super critical issue for any of this stuff is that the learning rate, right? Remember this eta parameter, which is like the step that we take in gradient descent, is super important to get good convergence. Right? And so we kind of drew pictures like this already, right? So let me just draw a couple examples of like weight versus error function, right? So say we're trying to minimize this function. I'm just trying to draw it 4 times here. So, you know, if my, and this is like the optimal weight that I want to find. So if I start here and I take like super duper small steps, right? This is like saying that eta is, you know, too small. Convergence will be super slow, right? So if I took a minuscule step every time, yes, eventually I would get there, but it would take me way, way, way too long, right? Kind of what I want, ideally, is that if I start here, I take like 1 step right down to the bottom, right? So this is like optimal step size, which of course you never know, right? That's the problem, is you never actually know how much of a step is safe to take, right? If you are kind of like within a good range, right? So if I'm kind of between the optimal step size and maybe some, you know, multiple of the optimal step size, what that means is that if I start from here, I'm going to like bang around until I reach the bottom of the pit, right? So this is kind of like, you know, this converges, but it's going back and forth, oscillating. And this is also potentially a slow process. And then if I make the worst mistake, which is I start here and I take a big step size, then maybe what may happen is I, you know, I'm going the wrong way and I'm taking huge step sizes and I bounce my way out of the bowl entirely, right? So it's a real challenge to figure out like how to make this step size thing work. And also, even though I wrote it like you're taking a single step along the gradient, in practice, you probably will also want to take like different steps along different dimensions of the gradient because the parameters may not be converging at the same time, right? So, you know, let us say that generally I may take a different step for each of the many parameters that I have. To get everything to converge at the same time. And again, that's like the ideal case, right? So kind of what you don't want is that some parameters are converged like 50 epochs ago and they would change, and other parameters are still changing, right? So kind of what you want is to tune your step sizes in such a way that everything kind of comes together at the last minute all at once, right? Again, there are principal ways of doing this that are kind of related to like the second derivative of your cost function. So one thing we talked about a little bit was, we talked about how if you think about the cost function as a bowl, you know, you can think about these second derivative methods that fit a little bowl to the area, and you can think about like if the bowl is really shallow, then I can afford to take a big step size. If the bowl is really narrow, I should take a smaller step size. And so you can kind of do this estimate at every point to decide what should I do. Again, not the kind of thing that you want to do manually, right? This is what the built-in optimizers in PyTorch and TensorFlow and so on are made to do, right? So we talked about there's something called the atom optimizer, which is kind of like, a fancy way of doing a version of gradient descent. The M in atom stands for momentum, right? So we also talked about momentum. I think I talked about this earlier in the gradient descent lecture. So this momentum keeps optimization moving even in what I would call flat regions of the cost function. So that's like saying that the weight that I choose is where I was. Normally what I would do is I would take a step in the gradient with respect to the backpropagation gradient. This is like saying here, this might be my normal backprop step. And then I add to that something that's basically saying I look at the difference between previous gradients and I add that here. So this is kind of like saying that, if the backpropagation gradient is close to 0, that means that none of the weights are going to change. But what I could do is I could say, well, I look at how much I changed before and just take it a little bit of a step in that direction also to make sure I don't just sit around 0 somewhere not moving, right? So again, one of the many ways that you can use this to keep your gradient descent going. And then finally, there are so many what I would call hyperparameters to tune. For example, the number of layers, the number of neurons in each layer, the type of activation function at each layer. Right? So when you're starting out with neural networks, you may be like, okay, should I use 3 layers or 4 layers or 20 layers? Should I use 500 neurons in this layer or 5, right? It comes with kind of intuition, and also there's no right answer, right? So it's, again, something where you just have to keep on screwing around with your network until you get what you want. And so luckily, most modern neural network training packages will have some defaults that are starting with reliable ideas for what the number of layers should be, what the types of activation functions should be, and help you quickly experiment with alternatives, right? So, TensorFlow and Keras and PyTorch and all those things, you don't have to make all the decisions yourself from scratch. You just kind of say, okay, I'm going to choose what the default is. If I don't like the default, I know the natural things that I could try to change, right? Like I said, even the most experienced neural network trainers spend a lot of time playing with the network, trying to get it to do better and better, right? And they face convergence problems, and they face, exploding gradients and vanishing gradients. You may be training and everything seems like it's great, and suddenly your network just blows up and you don't know why. So, this is the modern world, right? You may have to try a bunch of times to get this to work, right? And so that's why, again, we talked a little bit early on about, for example, the energy cost of training a massive system like GPT, right? So it's not like that they just had a cost function and trained GPT once and got to the error and then it got to 0 and they stopped, right? I'm sure there were hundreds and thousands of trials of changing architectures, changing parameters, changing step sizes, changing whatever to make it work the way they eventually wanted it to. So it's not like it was trained once. It was probably trained thousands of times. We'll never know exactly how many times it was trained, but that's something that I'm sure is a fact of life. So I'm not sure, like I said, I don't want to turn this into a deep learning class. I'm trying to think about what I can ask you on the next homework that will both test your understanding of neural networks without making it into some sort of a parameter tuning fest. So that's my job for next weekend, is to think about what would be a good neural net homework. And so what I want to talk about on Thursday is, okay, so this is like the most simple stuff so far that I talked about is like the multi-layer perceptron. Everything is connected to everything else in every layer, right? So you may have heard of some terms like, convolutional neural networks I mentioned. You may have heard of like dropout and attention and stuff like that. So I want to just kind of spend one lecture on terminology for modern deep learning type stuff, right? And that would be a great introduction to the deep learning class if you want to take it, which I believe is being offered next semester, right? And so that's probably a good entree into learning about all this stuff for real. And on all this kind of front, all of this type of stuff is still an area of active research, right? So like people like Dr. Tajer and so on in our department do research on, optimization of stochastic gradient descent in a way that works well, right? So there's still lots of active research that is just almost purely mathematical and doesn't have anything to do with, data and grungy data sets and stuff like that. So it's a very interesting, hopefully sphere that, again, if you want to learn about this stuff, there's plenty of ways you can go from here. So let's stop and ask questions or comments. Okay.